Well, hello and welcome again to our journey into number theory, and we finished up last time by stating Gauss's lemma, which I'll quickly just remind you of, and we did an example of that. So Gauss's lemma, you recall, says we start off with p an odd prime, and we take a and p relatively prime, and we form this set a, 2a up to a half p minus 1a. And then we read the numbers in here modulo p and reduce them. And then we count the number of elements in this reduced set that are greater than p minus 1 over 2. And then remarkably, the Legendre symbol is just equal to minus 1 to this number k. So this number is 1 if a is a square, and this number is minus 1 if a is not a square. So keep that in mind, and we're going to use Gauss's lemma to prove a very important result, and that is when is 2 a square modulo p. So again, p is taken to be prime in all of this, an odd prime. So for any odd prime p. And there's the formula. It's minus 1 to the p squared minus 1 over 8. You should convince yourself that p squared minus 1 over 8 is indeed an integer, because if p is an odd prime, then p minus 1, p plus 1, one will be divisible by 4 and the other one by 2, and so this is clearly going to be a whole number. Now, the reason this is important is that when we get to the quadratic reciprocity theorem, it works for odd primes when we've got a prime over a prime, but they both have to be odd primes. And so 2, always the bane of number theorists, but 2 is a pain, and we need a special case to deal with that one, and that's what we're going to do here. And also it's a nice application of Gauss's lemma, and it's also gives us a nice little lead in, I suppose, to the reciprocity theorem. So here's our little proof of this here. So we're going to prove that this formula tells you when 2 is a square, modulo p. Well, we start off in the usual way. We're going to take, so our a now is 2, so I take 2, 2 times 2, 3 times 2, all the way up to p minus 1 over 2 times 2, which is just p minus 1. So that's the set S we have to start playing with, and normally we'd have to reduce these numbers down modulo p, but happily in this case it's already reduced modulo p, so I don't need to reduce the numbers any further. So what we do is we now seek the number of elements in this set S, and they're all of the form 2x, and we want to know how many elements in this set are bigger than p minus 1 over 2. So that is, we now seek the elements of S of the form 2x, they're all 2 times something, that lie strictly between p minus 1 over 2 and less or equal to p minus 1. And the easiest way of doing that is to look at some cases. So the case 1 is I'm going to put p to be 1 modulo 8. We do that because it makes the calculations much easier, as we'll see. So if p is 1 mod 8, that means p minus 1 is a multiple of 8. It's 8 times L for some L in some integer L. And if I plug that back into this important inequality here, then I simply get that. And I can happily divide everything by 2. I get this. And now it's easy to see that there are 2L numbers between 2L and 4L, excluding 2L. And so in this case, 2 over p is minus 1 to the 2L, and that's even, so you just get 1. Now you can do a similar case, which I'll leave you to do, similarly for p is minus 1 modulo 8. So you do exactly the same thing. You'll get p plus 1 is 8L, and you've got to do the similar calculations, and you'll find that 2 over p is 1. So that means 2 over p is, so 2 is a square modulo p at the moment if p is an odd prime congruent to plus or minus 1 modulo 8. Well, the other case is if you've got a prime and you're working modulo 8, then the only possibilities are 1 and minus 1, or 3 and minus 3. That is 1, 3, 5, or 7. So we now look at case 2, where p is congruent to 3 mod 8, and in that case p minus 1 is 2 plus some multiple of 8 for some L in integer. Again, we plug this back into our basic inequality we had before, and we get this here. Now, one wants to divide by 2, but this is odd, and so I just sharpen the inequality here and say, well, look, this is bigger equal to 2 plus 4L. And now I can happily divide by 2, and I get this. And now the number of numbers between 1 plus 2L and 1 plus 4L, including both the endpoints, is 2L plus 1, the plus 1 of course for the extra number here. And this is an odd number, and so in this case 2 over p is minus 1. It's minus 1 to this power, which is odd, so you get minus 1. And I claim that similarly, if you do the case for p is minus 3 mod 8, you might like to try that yourself, you also get minus 1. So we can summarize that then as 2 over p is 1 if p is plus or minus 1 mod 8, and minus 1 if p is plus or minus 3 mod 8. Remember what that means. That means 2 is a square if and only modulo an odd prime p, if and only if the prime is plus or minus 1 mod 8, and it's not a square if it's plus or minus 3 mod 8. So again, we're seeing this sort of the primes falling into different classes. Primes of different shapes do different things, and here we're looking at the primes modulo 8. Now you can combine all this together in one go by writing it like this, which you need to perhaps just think about. If p is plus or minus 1 mod 8, then if you plug that into here, you'll simplify it, you'll get an even number, so you get 1. And if you have a prime that's plus or minus 3 mod 8 and you plug that into here, you'll get an odd number, so you get minus 1. So this is just a clever way of rewriting what we discovered by using Gauss's lemma. Okay, so I thought I might just do a little example just to play with this a little bit to show you some interesting things you can do. This time we're going to look at q as an odd integer, and we're going to take a prime p, which is a 12 times my q plus 1. I'm going to assume this p is prime. So for example, if q was 3, then you'd get p is 37, which is prime. Doesn't always work, of course. If you take q is, it's got to be an odd integer, so if you took q as 4, for example, this is not going to be a prime, but in the case when this is a prime, for q odd, then we're going to take this prime and call it p. And we're asked to do a number of things: to evaluate the Legendre symbol, to see when 2 is a square, or see if 2 is a square mod p. We're going to get this little identity here, and we're going to use that then to find a prime factor of 2 to the 78 plus 1, which is nice because this is a fairly large number and it's not prime. In fact, you may recall that for a number of this shape to be a prime, it is necessary but certainly not sufficient for this number up here. Has to be a power of 2 anyway, so we know this is not prime, but we want to get actually a prime factor of this one without actually looking at the number itself. So it's a nice little application here. So let's just work through this one here. So here we've got what q is odd and p is 12q plus 1, and we're assuming this is a prime number. So we hit it with our lovely formula that 2 over p then is minus 1 to the p squared minus 1 over 8. I factor the p squared minus 1, and then I can plug this in its place. And so I simply get that. I can do some simplification here. I can take a 4 into there and a 2 into there, and I get 3q times 6q plus 1. Now remember, q is odd, so that's odd times odd, and this is odd, so this power up here is odd, so you get minus 1. So that means the Legendre symbol 2 over p is minus 1, i.e. 2 is not a square modulo this prime p of this shape. So for example, as I said, if q is 3, you get 37, so you can say that, for example, then that 2 is not a square mod 37. Now I can immediately then use Euler's formula. So Euler's formula says that 2 over p is 2 to the p minus 1 over 2. And if I plug in that in terms of this q, which is 12q plus 1, then I get 2 to the 6q, but we worked out what this was before. It was minus 1, and so that one is equal to minus 1. So 6 to the 2q is minus 1 mod p. Sorry, 2 to the 6q is minus 1 mod p. And if we now put q is, say, in order to look at 2 to the 78 plus 1, then I want 6q to be equal to 78, so take q to be 13, and that fits all the criterion. Q is odd. If you take p to be 12 times 13 plus 1, you get 157, which of course is a well-known prime. And that means then that this p is a factor of, because we've just seen that 2 to the 6q plus 1 is divisible by p, so this prime 157 is a factor of 2 to the 78 plus 1, and that just follows as a consequence of part 2. So there's a nice example of where we can find a prime factor of a large number without actually doing any division or looking at the number itself. Nice, just a nice little example there. Okay, we come now finally to the law of quadratic reciprocity. This was Gauss's, really one of his great discoveries. Gauss gave numerous proofs of this during his life, but the proof we're going to look at actually comes from one of his contemporaries, a younger contemporary, Eisenstein, and that's the one we're going to have a look at. So let me just explain to you what this says. It's really telling you a connection between the Legendre symbol p over q and q over p, where p and q are odd primes. Now the odd is very important here. This doesn't work if either p or q is 2, and that's why we needed that earlier special case. So to put this into English, this says if you've got a prime, which is, you've got 2 primes, and if one of them, doesn't matter, you can have both, or you just need at least one of the 2, is a 1 mod 4 prime, then p is a square mod q, if and only if q is a square mod p. P is a square mod q implies q is a square mod p if either p or q are 1 mod 4, and if both of the primes are 3 mod 4 primes, then p is a square mod q means that q is not a square mod p. That is a beautiful, remarkable result due to Gauss. Whether it had been guessed before him, it probably had been. You wonder if Fermat perhaps had a rough idea about this, but had no idea how to prove it. And you can combine these together, much as we did before with the 2 over p Legendre symbol, and you can write this as p over q is q over p times minus 1 to the p minus 1 over 2 q minus 1 over 2. So I leave you just to check that if either of these is a 1 mod 4 prime, then whichever it is, that will make this index here even, and so you'll just get p over q as q over p. And if both of these are 3 mod 4 primes, then this will be odd, and so you get this case here. This is just a cute way of writing it, but actually turns out in terms of our proof here, it's a useful, very useful way of writing it, because this is what we're going to prove in the proof of the quadratic reciprocity theorem. So I'm going to just, before we do the proof of this, I want to do an example to show you how this works. So we're going to evaluate 521 on 997. That is, we're going to ask the question, is 521 a square modulo 997? And I have to tell you that both of these numbers are prime. You can check that yourself, but both of these happen to be prime numbers. So there's our Legendre symbol, and 521 you can see is a 1 mod 4 prime. And I'll see that pretty quickly, because if you subtract 1, the last two digits are 20, which is divisible by 4. So that one is a 1 mod 4 prime, and so I can flip the symbols around. So I can interchange these two. Now the point about that is I can then read this one modulo 521. So I take that minus that is 476, and so I can now, you see the numbers are getting reduced, and I've now replaced the denominator here, which was a larger prime, by a smaller one. Now this number here, of course, is not prime, and so what I'd now do is I'm going to factor this, and it happens to be divisible by 4. And if you divide this by 4, you get 119. So what I'm doing here is I'm actually splitting this as 4 over 521 times 119 over 521. And then 4 is a square, obviously, it's 2 squared, so that value is 1, and it just reduces down to this. Now, you can factor this further, in fact, because this turns out to be 7 times 17, and so what I then did was I factored this further as to 7 times 17, so that I get primes again. These numbers must be primes in order to use the odd primes in order to use the reciprocity theorem. So the 521, remember, was a 1 mod 4 prime. I just need one of these two to be a 1 mod 4 prime, so I can flip it upside down. And that's a 1 mod, in fact these are both 1 mod 4 primes, I can flip it upside down. And now I can read 521 mod 7, which is 3. And I can read 521 mod 17, which is 11. And you see how I've broken this the numbers are much smaller now. Now in this case, 7 and 3, these are both 3 mod 4 primes. So when I flip these around, I get a minus sign. 17 is a 1 mod 4 prime, so I can flip that without penalty. And now 7 over 3, well, modulo 3, 7 is just 1, and 1 is a square, so 1 over 3 is 1, so I just get the minus sign here. And 17 mod 11 is 6. Finally, I can split the 6 up into 3 times 2. These are both 3 mod 4 primes, so when I flip this upside down, I pick up a minus sign, which cancels to give me a plus there. This one now, this is a 2 on the top, so you can't use the reciprocity theorem, so you go back and use that lovely formula. It's a minus 1 to the 11 squared minus 1 over 8. And that's 120 over 8, which is 15, and minus 1 to the 15 is minus 1. And this one I can read modulo 3, I get 2 over 3, and times minus 1. And 2 is obviously not a square mod 3, because the squares modulo 3, the only numbers are 1 and 2, and they both square to give 1, so 2 is not a square. So this is minus 1, just by inspection, and you get 1. And so that tells me that 521 is a quadratic residue, that is, it is a square modulo 997. And so there's a nice little example of that. Now in the next video I will go through the proof of a proof of the quadratic reciprocity theorem. I'll go through the one that's due to Eisenstein.